In the next module in Chapter 33, Module 33.3, we wish to discuss the energy and momentum that are carried by an electromagnetic wave. We'll not spend a lot of time on this at this level in the course, but there is an energy density, U, that is 1/2 epsilon naught times E squared plus 1/2 mu naught, and the mu naught is in the denominator here, times B squared. This right here is the energy density at any point in space. And you'll notice here that it is the square of the electric field that gives us this energy density and the square of the magnetic field, apart from these constants. So when I double the strength of the electric field, as usually happens with a wave, if I double the amplitude, then I multiply the energy density by 4. It carries 4 times as much energy. And in general, the amount of energy that's contained in the electric part and the magnetic part is equal, although that's not exactly apparent from this equation here. Now, for an oscillating field, we have to use the root mean square, which means that since this field is alternating like this, we just get kind of an average of this, and that average, E root mean square, is actually the E naught that we have that makes up this E when it's multiplied by the cosine. If we average it out, we have this over the square root of 2. And therefore, when we square the electric field, we get a factor of 1/2 as much. So we get E naught squared over 2 here, as well as that 1/2 that's in front. Likewise, we get the same thing for the B field. There's a second part of this problem. Let me move this page up some. And the second part of this is the intensity of the electromagnetic wave is given by the power per square meter. This is like the radiation power that would be in watts per square meter from sunshine or something else. And this is expressed as S. It has a direction, and so it can be thought of, and it's always given by the velocity of light times the energy density, where the energy density is given by this form here. So whereas this is the energy density, if I multiply that by C, I get the power per square meter. And so this becomes a very useful equation for looking at the wattage per square meter that we have from electromagnetic wave.